接下来我们要next we are going to talk about more on complex number and its relationship to impedance. And last time I remember that we say that the impedance of capacitor is 1 over j omega c, and the impedance of the inductor is j omega l, where c is the capacitor value and l is the inductor value, which the units is Henry or Farad. Okay, that is a long story about why we want to use complex number to represent the resistance, and the real and imaginary resistance. Usually, these two combined becomes the we call impedance. And impedance, it has the real part and the imaginary part, and that's why we in the capacitor and the inductor we have the J here, which is the imaginary part. Okay, this is the imaginary part, and the J is equal to square root of -1. And here we use I, but most of the time in engineering we use J. Okay. Then I want to talk about this problem more, and one of the reasons that we introduce a complex number mainly because especially in this course, not every course, but especially in this course, it is because we have the function called that's e to the j omega t. Okay, and e to the j omega t based on Arrow's formula. Okay, is equal to cosine omega t plus j sine omega t. And mostly we know that because the exponential of x will be equal to, the derivative of the exponential x will be equal to exponential equal to itself. This one is d, the e, and the dx here. Okay, and the x here, and the t here, are independent variables. Okay, and so you can regard this one and then this one, both these are sinusoids with frequency omega, and which is equal to 2 pi f, and omega is a radian per second, and the f will be hertz. Okay, and why this is we use imaginary part of that. The reason why the reason to use the complex number is in the behavior of the capacitor inductor are quite different from the resistors. For example, for a resistor R, okay, we know R will be equal to V over I, and the R is a real number. So even the voltage is a function of time, and the current is also a function of time, but the relationship after V divided by I, okay, is still a real number, and this number doesn't change. it doesn't change. With respect to time and the frequency. Okay, so this is also a real number. Okay, but the capacitor and the inductor are a little bit different. Let's first talk about the capacitor. Okay, for a capacitor C, okay, if the voltage across the capacitor is V C of T, and the current flows through the capacitor is IC of T, okay, and the relation between the relations between the VC of T and IC of T becomes the will be equal to IC of T. That's its relations. And VC of T, if we make it directly divided by IC of T, is not a real number anymore. So it's more complicated, as we can see. Okay, because of the derivative here, so mostly we'll talk about the VC of T and IC of T are both time varying. Okay, that makes things a little bit difficult. Okay, so how to do it? Okay, so we can no longer represent the resistance. Of course, the name resistance is not appropriate, but we still use it now, of a capacitor is not fixed anymore. Okay, it will change. So how to find the resistance of the capacitor? Well, after we use the complex number system, we change it to impedance. Okay. Actually, the good name should be the impedance. All right. Okay. So a very interesting thing to solve this is that we apply the Fourier transform in this part. Okay, because we have a derivative here. We have the derivative here. So this one become actually a differential equation. And if you have ever learned the engineering math, then we know how to solve it by differential equation. But since we don't have that kind of tool to do it, so at this moment I try to use another way to explain this. So we introduce something called a Fourier transform. Of course, you don't have to know lots of the detail about Fourier transform. I just try to use Fourier transform to explain why the impedance of the capacitor is 1 over j omega c. Okay, so let's first introduce what is Fourier transform. In a Fourier transform, f of omega, well, actually is defined by the ft e to the minus j omega t dt, meaning that this is the time domain signal, and this is the frequency domain. Signal. But these two are the same. meaning that f of omega, it is 1 to 1 to f of t, meaning that if the ft is fixed, then f omega is fixed. Okay, this is the Fourier transform, meaning that if you find the ft, then f omega should be you can find the exactly the same omega. So if we have the condition is ft is equal to g of t, then f of omega gotta be equal to g of omega. Okay, that's the reason. There are some there are some assumption such that the Fourier transform of ft is this. Okay, but we are not going to talk about that. I just want to use the Fourier transform to explain the impedance of the capacitor. So let's see. So if since we have a Vc of t, but we have a term which require derivative of Vc of t. So if also I take the Fourier transform of the derivative of Vc of t, which is to the minus omega t dt, and in calculus we can use a special formula. This one, if we have f multiplied by the g, okay, it will be equal to f prime of g plus, let me write more clearly. If I have the function f of t multiplied by g of t, then the derivative of f of this function will be f prime of t multiplied by the g of t plus f of t multiplied by g prime of t. Okay, so I can try to do this. So let's assume that Vc of t, okay, is f of t. Then let's assume that e to the minus j omega t will be the g of t. And we can apply this formula such that this one becomes not that fast. So we can have the VCT, the e to the minus omega t, its derivative will be equal to the VCT dt e to the minus j omega t plus Vc of t e to the minus j omega t, but its derivative. And I can further write this one, Vct dt e to the minus j omega t, and because the e to the minus j omega t, if I take a derivative, it will be minus j omega e to the minus j omega. Sorry. This one will be minus j omega multiplied by e to the minus j omega t. So I can just write it here. So I can make it here. So this is minus j omega Vct e to the minus j omega t. Okay, if I integrate both sides, what will it become? Okay, we will find that this is the one we want, this one. Compare this one with this one, right? Okay, so the VC dt e to the minus j omega t dt will be equal to VC t e to the minus j omega t plus j omega VC of t e to the minus j omega t dt, right? So there is a condition. If VC of t will be equal to 0 when t goes to infinity and t goes to minus infinity, then this term vanish to 0. Okay, this is important conditions. And usually we can make this assumption. So the dvc dt e to the minus j omega t will be equal to simply the minus j omega vct e to the minus j omega t dt. And what is this? This one is j omega vc omega, okay. And this one is the Fourier transform of vc of t. So let's go back to the differential equation. We say C dvc t dt will be equal to IC of t. So if we take the Fourier transform from both sides, then we find this one will be j omega c multiplied by the v omega, right? Vc of omega. And the right hand side become the IC of omega. So if I just move around, I find the Vc of omega over IC of omega will be equal to 1 over j omega c. So if omega is fixed, then 1 over j omega c is fixed. So unlike if you take a this one, this one is not fixed because Vc of t and IC of t, okay, are time varying. Okay, but this is the very good condition is that if we try to analyze a signal with specific frequency, then its impedance is fixed. Okay, and from this we find the j omega c. This one will go to 0 if omega goes to infinity. And when it goes to 0, it's something like a short. Meaning that for a capacitor, if the input frequency is very, very large, then it's act like a short circuit. But if it goes to infinity, if omega goes to 0, so for this one, it becomes like an open circuit. So it's something like an open circuit. meaning that for a very low frequency signal, a capacitor just acts like an open circuit. And this is the reason that we want to introduce the complex number. And same thing to the same thing to the inductor. For the inductor, L, we also have the VL of T and the IL of T, right? And for the inductor, the differential equation is a little bit different. For the inductor, the L, the differential equation becomes ILT dt will be equal to VLT. Okay, meaning that if we have a change in the current, we create a voltage. So let's play the same tricks. We take the Fourier transform for the both side. Okay, then what do we have? We have L, J omega L, the IL of omega will be equal to VL of omega, right? So VL of omega divided by IL of omega will become J omega L. Okay, so for the J omega L, it will go to infinity when omega goes to infinity. Means for very, very high frequency signal is like open. Okay. And on the contrary, its impedance will go to 0 when omega goes to 0. Okay. So if for a very low frequency signal, this one like a short circuit. Okay. Then we have the two new things. We have a complex number resistance, which called impedance. So if I have a circuit something like this, R, and for example we have an inductor here, and now we no longer use then this is L, and we no longer use a real resistance. Now we use impedance, and we know that the impedance of the L will be equal to J omega L, and so the combined equivalent circuit, we have something new. For example, we can just draw something like this. This is the equivalent element, but with impedance. With impedance equal to R plus J omega L. So even you have a signal connect to a bunch of, for example, a bunch of a circuit like this, even if you have something quite complicated, something like this, we can still write an equivalent an equivalent circuit, something like this. And the equivalent, this is an equivalent circuit, okay. And this is the element that we have the impedance. Okay, equal to, for example, R, which is in the real part, and R in the imaginary part, sorry. Let me use XY. X plus JY. Okay. And this part is from, they are from resistors. But this part are from capacitor and the inductor. Okay. And actually, how large is the impedance? How large is impedance? Usually, we if we want to see what's the magnitude of the impedance, we will say sometimes we just make it x squared, y squared will be equal to 1. This will be the magnitude of the impedance. Okay, so that's what we have. And then we have the impedance of capacitor and impedance of resistor. Then we will know how to calculate the frequency response of a filter, and we will talk about it later in the next recording.